So, we are back. Okay, shall we start?
Yes, sir.
Okay, so I was trying to explain you that why Cartesian robot has SLI, structural length index, equal to 3. So, go to this paper where I was deriving. So, you have AI plus BI. Now, for a Cartesian robot, for Cartesian robot arm, if you write the DH parameters, okay, you can see that AI values. So, you have BI, theta I, AI, alpha I. You should be able to see that they have zeros and B1, B2 and B3, okay. So, which we are assuming as a B, okay. So, this will be your 3B, okay. Now, the workspace, since it can go B in these directions, so we will have a box, we will have a box, we will have a box which is the workspace. So, this will be workspace, and the volume of the workspace is B cube, right. So, if you write QL is L by square root of W. So, L is 3B and cube root of B cube is 3. So, cube root of B cube is 3B by B, 3 by B. So, QL is 3. So, which means for generating the workspace, this much of workspace, okay, and what is the link length is required. So, QL is an index to tell that it requires 3 is the QL for the articulated the Cartesian robot arm. If you want to do for the articulated robot arm, this can be calculated from so this can be calculated for articulated robot arm, for articulated.
Hello, sir.
Yes.
Hello. Last slide.
Okay. So, L is my length sum AI plus BI, AIs are zeros, BI I am assuming B1, B2, B3 all have the same length variation, which is B, B and B. So, this is 3B. The workspace is B cube, QL is L cube root of W. So, L is 3B and cube root of B cube is B. So, this is 3. Okay. Now, if you want to do in a similar fashion, you can try yourself for articulated arm. I can show that QL should be equal to cube root of 4 pi by 3. Okay. You try to verify this. So, this will be 0.62. So, this means it requires very little link lengths to achieve a large workspace. So, these indices is SLI, structural length index, if it is low, then this says that you require less link length for the large workspace. So, we go back to the slide. So, Cartesian robot SLI 3 means I require more material, which means my robot becomes a bulky one. Okay. And so, obviously, it will be more expensive. Then articulated one 0.62, it is better than the Cartesian one because it will be much lighter. But I told you once, nothing comes free. So, here we have seen already some advantages. Here we have seen some advantages. The 3 orthogonal joints, very stiff, very large robots, decoupled, no singularity, but you pay this price, more material and bulky. Whereas for Cartesian robot has singularity, and mathematically it is more complex, as we have seen during our kinematic study, but it has advantage that it requires very little material for the design. Now, let us do an example for a Scara manipulator. Again, this is taken from the example of the book. Scara manipulator is this one. So, this is the Scara manipulator we are talking about. It has a link length here, it has a link length here. Assume both the link lengths are same. Okay. So, we assume the length of 1 and 2 has a by 2, range of motion of the prismatic joint is B3. So, this motion we assume B3. Find the minimum QL. Okay. So, what is the minimum QL you can achieve for Scara manipulator? So, I first find the length sum A2 plus A2 plus B3, because there are 3 joints, that gives me A plus B3. Okay. So, this is wrongly written, this is not length sum, 1 minute, this will be SLI. So, SLI QL is given by A plus B3, which is L, and since the shape of the workspace is cylindrical, so pi A square will be the area, cross sectional area, and B3 will be the height. So, for the cylindrical workspace, now let us go back. So, this length is A by 2 and this length is A by 2. So, if it stretches, so when it stretches, this takes this much space. So, this distance from here to here is A. So, when it moves, it will create a circle like this. So, this is pi A square, and then this will be height B3. So, the cylindrical workspace is pi A square B3. Okay. So, this is now the expression QL, A plus B3 is Q root of pi A square B3. Now, I am looking for minimum QL. Okay. So, minimum QL I can differentiate with respect to a function B3 by A. Let me do it for you on the paper. So, QL I have calculated as A plus B3 cube root of pi A square B3. Okay. So, I introduce B3 prime as B3 over A. Okay. So, then what I do is I do A plus B3 over A, and then cube root of pi a square b3 over a. Okay. So, then this becomes 1 plus b3 over a, and then I do this thing cube root of pi a square b3 over a cube. Okay. So, this square and this thing will go. So, this will become 1 plus b3 prime, okay, and this will become cube root of pi b3 prime. Okay. So, now I do it like this: 1 over cube root of pi is my constant term, then this becomes 1 over b3 prime to the power 1/3 plus b3 prime, this will be b3 prime 1/3. Okay. So, this I can write 1 over cube root of pi, so b3 prime minus 1/3, okay, plus b3 prime. So, 1 minus 1/3 will be minus of 2/3, 3 minus of 4. Okay. So, QL is written as 1 over cube root of pi b3 prime minus 1/3, and this will be 1 minus 1/3, 3, sorry, this will be 2/3. Okay. This, let me rewrite this portion again. I will rewrite 1 over cube root of pi, this I will rewrite in the next page. So, QL will be 1 over cube root of pi b3 prime minus 1/3, and this will be plus b3 prime 1 minus 1/3. So, this will be 2/3. So, I cube root of pi b3 prime minus 1/3 plus b3 prime 2/3. Okay. So, now I can find out the minimum QL. So, to find minimum QL, I do perform del QL del P3 prime is 0. This you know, this is the condition of maximum or minimum. So, now if you do this one, so this will become 1 over cube root of pi minus 1/3 b3 prime minus 1/3 minus 1, then plus 2/3 b3 prime 2/3 minus 1 should be equal to 0, right. So, from here 1 over cube root of pi minus 1/3 b3 prime minus 4/3, this will be plus 2/3 b3 prime. So, this will be 3 minus 1/3 equal to 0. Since this is a constant term, this cannot be 0. So, this has to be 0. Okay. So, now from here we can very easily see that minus 1/3 of b3 prime.
Yes, sir. Last slide.
Last slides. It is for you now. So, I am just doing the differentiation with respect to b3 prime. Okay. So, here minus 1/3 comes coefficient, minus 1/3 minus 1 differentiation rule, 2/3 here 2/3 minus 1 is the differentiation rule, and then minus 1/3 minus 1 minus 4/3, 2/3 minus 1 it is minus 1/3. Okay. So, now this coefficient has to be 0, which means minus 1/3 b3 prime minus 4/3 should be minus 2/3 b3 prime minus 1/3. So, minus 2 by 3 B3 prime minus 1 by 3. Okay. So, now this minus plus 3 gone. So, now we will have 1 upon 2 is B3 prime minus 1 upon 3 and then divided by B3 prime minus 4 by 3, which is equal to B3 prime minus 1 upon 3 plus minus 1 upon 3 plus 4 upon 3. So, this will becomes B3 prime. Okay. That should be equal to half. So, B3 prime means B3 by A. So, which means B3 is equal to A by 2. So, when B3 is A by 2, QL is minimum. Okay. And what is the QL value? I now substitute QL is equal to A plus A by 2, then cube root of pi A square and A by 2. So, this will be 2 3 by 2 3 by 2 A, this will be A cube root of pi and this will be pi by 2. So, this A cancels out, this will be 1.5 and pi by 2 is 1.57, okay, cube root. So, this result will come out to be 1.29. So, if you want to know the QL, structural length index of a Scara robot, which will vary as the prismatic joint moves up and down. So, in this exercise we have found out what will be the minimum value for QL for a Scara robot, that we have calculated. It will be minimum when B3 is equal to A by 2 and the minimum value is 1.29, which means even for the minimum value of QL, this is not as good as articulated robot, it is better than the Cartesian robot. So, 1.29 means it will still require some link lengths to obtain a certain workspace. So, so far what we have studied is how to determine that how much link length we have to provide in order to obtain a certain workspace. So, that is one measure of that how much material we should put for a certain workspace. Now, we would look, once we have developed then what is the quality of the job it will perform, that will be depending on based on the workspace singularity. So, let us go to the slide. So, workspace singularity we define where end effector cannot reach. We should be knowing from our design that these are the places inside the workspace it cannot reach, and this concept we have already introduced during our statics. The twist of the end effector means angular velocity and linear velocity of the end effector can be related to the joint rates in terms of Jacobian. If the determinant of Jacobian is 0, or alternatively we call condition number of J is infinite, then those positions cannot be reached. In this connection, if the condition number J is 1, this is the best one can achieve. Okay. So, let us see for a simple example of two link arm. We have seen during statics which are the good positions, and we will see in terms of the velocity also they remain as the good positions. Now, this is the Jacobian of a two link arm. Okay, here it is shown. This Jacobian we have calculated. Determinant of Jacobian we also calculated as A1 A2 sin theta 2. this is this angle. If theta t equal to 0 or pi, 0 or pi means when they are stretched. So, 0 means this is 0 stretch conditions, and pi means this condition. Okay. So, second link is stretched or folded in. That means at these positions it cannot go there, it has only velocity only tangential to this link. So, using this information of J, we can bring the concept of manipulability. Earlier in statics we studied statics force ellipsoid. We have studied force ellipsoid in statics, but in here in velocity we bring the concept of manipulability, how easy to manipulate. So, where end effector should behave best. A good manipulability of a robot will tell that these are the areas where end effector will behave best. This can be obtained by forming this kind of relation. Twist of the end effector transpose, twist means velocities, transpose velocity 1 will give me an equation of an ellipse. Okay. And there if the condition number is 1, condition number of this one is 1, then we can find out that some configuration, that means theta 2 is 3 pi by 4 for this kind of link length ratio. The condition number will be 1 and it will be best configuration. Look at my hand here. Suppose this is my link 1, this is my link 2. So, theta 1 is 0, theta 2 is 0, right. Now, theta 1 is 0, theta 2 is pi, and here theta 2 is 3 pi by 4. Now, imagine now this is, if you want to have a heavy weight, this is my best configuration. I can have a heavy weight lifted in this configuration. You never lift in this way, right. So, this is the best positions one can have. So, theta 2 90 and theta 2 135, 3 by 4. So, this is the best configuration in terms of force can be obtained, and this is the best configuration to go any direction. You want to go in this direction with certain velocity, you can easily go. You want to go to this direction with certain velocity, you can easily go. You can if you want to go to this direction with certain velocity, you can easily go. So, in terms of velocity, this is the positions from where you can go to any directions with certain velocity easily. In terms of force, this is the best positions to hold any heavy object. So, the meaning of isotropic or meaning of condition number of J transpose J on my LCD screen, best means what I explained, and they are called isotropic points. Okay. Now, I can draw certain plots for a 2 revolute arms. You can see this J transpose J, it is the equation of a ellipse. That ellipse at the center becomes a circle, and along the edge it becomes a almost like a line, which means at these positions, maybe at these positions, no, maybe at these positions, at these positions, they behave best. So, theta dot J transpose J, theta transpose J transpose J theta dot is an equation of an ellipse. Major and minor axis are related to the eigenvectors of J transpose J. If you do not remember much of eigenvectors, do not worry much. Center of the workspace has the best circle. So, this is the workspace zone. This is the workspace zone, and around the center it is the best space. This concept can be extended to force and stiffness ellipsoid as well, which we have already studied. Okay. And So, today I will stop here. This actuation scheme I will take in the next class. Now, if there are quick questions, I will take the questions. Before that, let us put the summary. We have talked about the task requirements of a robot. Kinematic configurations like articulated Cartesians are explained. Structural length index is introduced, and an example corresponding to a structural length index of a Scara robot is solved, and the manipulability is defined, and a relation with respect to force ellipsoid is also given. Actuation scheme we will do in the next class. If there are general questions, please ask. I will wait about 30 seconds for the general questions. Otherwise, these 6 students will come in the front and then show me my 4th assignment, which is related to the Jacobian relation from the 4th frame to the 1st frame for 3-link revolute arm. Okay. So, if there is any general questions, please ask. Otherwise, these 6 students please come in the front bench. Lik Kinfu, is he present? If not present, can somebody, okay, fine. Come in the front bench. Lik Kinfu, raise your hand. Mebrit Ambaye, okay, good. Meheretep Kebede, raise your hand. Okay, fine, come in the front bench. Mesai Alemu, please raise your hand. Okay. Nestanet Desaleng, please raise your hand. Nestanet Desaleng, okay, good. Samson Zarihun, please raise your hand. Okay. So, all 6 are present. Now, Like Kingfu, show your assignments of 4. Okay. Okay. Can you take the mic? Please take the mic. Okay. Can you hear me? Okay, I can see this. Can you hear me?
Yes, I can hear.
Okay. Is there any difficulty to solve this?
Actually, it is already solved in the book. There is no difficulty.
It was solved in the book. No difficult. Okay, fine. The next student, Mebrit Ambaye. Okay. So, you copied from the book? Please answer my question. Did you understand what was done in the book? Did you understand what you did? Switch it on. Yes or no? Did you understand what was solved in the book?
Yes.
Okay. Did you copy or you did yourself?
I did it by myself.
Okay, very good. Next, Meheretep Kabede. Thank you. Okay. Okay, please bend down so that I can see your face also. Okay, I can see it. So, is there any difficulties?
No difficulties.
You have any question to ask me?
No questions, sir.
Shall I ask you a question?
Yes, you can.
Okay. From dynamics?
From statics,
From statics. Okay. What is the good positions for the force ellipsoid becoming a circle?
surface,
Force ellipsoid sometime becomes a circle based on the configurations, right?
yes.
For a two link revolute arm, what is the positions when it becomes circle?
I don't understand your question, sir.
Okay, you
What
go
was-
the force ellipsoids. You understand force ellipsoids?
Yes, sir.
Okay, when the force ellipsoids become circle,
When the eigenvectors are the same, I think.
not at the end,
Equal.
not at the end it becomes a line.
Eigenvectors.
Okay, thank you. So next one, Messe Alemu. Show me the last page. Show me the last page. Bring it down. Bring it down. I am seeing only white. Bring it down. Okay. Tell me 1, 2, 3, 4, 5, 6. Why there are 6 rows? Because it is a 3 degree of freedom robot. It should have 3 by 3 Jacobian, right?
Yes.
Why you have 6 by 3 Jacobian?
Identity 0.
Okay, so you should delete the zeros.
Yeah.
Okay. Okay, next. Nestane Desalegn. Okay. Show me the second page. Okay, next page. Next page. Bring it down. I wanted you to complete it with the elements. You have not completed with the elements. Right? Q1 will have. So you please complete it, right? Okay, next. Samson Jerihon. Show me the third page. Okay, why there are 6 rows for a 3 link revolute? It should be 3 by 3 Jacobian, right?
I think because the range value of W is a 6 by 6 matrix.
Yeah, so you have to remove the zeros corresponding to 2 rotations and 1 translations, which is not possible in a planar case, right?
I didn't understand. I think so.
For a when we treat a 3 link planar robot as a 6 link during our Jacobian, right? But actually the robot has 3 degree of freedom. So the top 2 rows of the Jacobian corresponding to rotations about x axis and y axis, which are not possible, right? So for the final expressions you should remove those zeros rows and produce the final 3 by 3 Jacobian matrix. Is that clear? Okay. Okay, thank you very much. If there is a quick questions, you can ask me, otherwise we will say bye bye. Any question? No? Okay, thank you. See you on Friday. I will come back on Friday, not Thursday.
Hello, sir.
Yes?
I
Question?
have a question.
Yeah, please.
Can you explain the concept of singularity and its effect on Jacobian indices?
Okay, it is the other way around. When the Jacobian, when the determinant of the Jacobian is 0, then we call the robot is singular. Okay, I will spend maybe a little more time in the next class at the beginning. Okay.
Thank you.
Okay.